All right, everyone, welcome back. Today we are talking about speed versus velocity. Last time we talked about speed, but today we're going to be talking a bit more about velocity and how that works in physics. So speed is, as we talked about last time, distance divided by divided by time, and it's always a positive number. It has the distance and time, which speed is, like we talked before, is a scalar, so it only talks about the magnitude, not the direction. However, velocity is the ratio of displacement and time, and it's a vector quantity, so it implies a direction. So it can be positive or negative because the negative can imply going to the left, going west, or going south, while positive can imply going to the right, going up, going to the east, and so on. Formula of velocity is the displacement divided by time. We talked about displacement. Again, that's the part. Displacement can be positive or negative. And we have it annotated like this: V equals in change in x, or change in position, divided by time. Okay, so let's get started with this. First of all, let's talk a little bit about manipulating formulas. So we have the main formula here: speed is equal to distance divided by time. And if you look at this triangle here, it can kind of, I hope it can kind of make sense to you. So speed is equal to the distance divided by the time. Okay. And then another way to look at it, let me change this, is let's look at time now. Time here is equal to the distance divided by the speed. Okay. So this is a little, if you have trouble with the algebra, this is something that you can do. But now let's look at the distance. So distance is equal to speed times time. Okay. And again, you don't have to use this. If you're good with the algebra, you don't have to do this. But if not, this is a little trick to help you with knowing how to manipulate the formulas. Okay. If you're looking, if you're not looking for speed, or you're looking for time instead, or distance, then you can do that. And if you're wanting to do like velocity, it's the same thing. You could just cross speed out and do velocity, and you cross distance out and do displacement, and time is the same. All right, so let's start doing some problems. Okay, example number 7. Cindy sees an ice cream truck and charges toward it toward the right. She runs 60 meters in 8.2 seconds. What is her average velocity in meters per second? What is her average speed in meters per second? Okay, again, we're going to underline keywords. 60 meters, 8.2 seconds. Okay, next thing is you want to draw out the problem. Luckily, a lot of this is drawn out, but I'm going to draw the finer details. So 60 meters in a time of 8.2 seconds. Okay, part A is just the velocity, and this is equal to the displacement divided by time. Okay, and it looks like, Cindy is just going in a straight line, so we can do the displacement is equal to 60 meters and divided by 8.2. And let's put this in our calculator and see what we get. 60 divided by 8.2, and we get 7.32 meters per second. And I can leave it like this, and this would be correct. The positive implies that it is going to the right, or I can say 7.32 meters per second to the right. Okay, and this would also be correct. So whichever one is better. Part B is, what is her average speed? Speed is equal to distance over time. And in this case, and in a good amount of cases, the distance and the displacement is the same. So we have 60 divided by 8.2, and we have again 7.32 meters per second. Okay, again, speed does not need direction, so it's always going to be positive, and you don't have to write which way it's going. Okay, next example. Jim sees a spider and lets out a loud scream. Then he starts running away as fast as he can to the left. He travels 20 meters in 10.2 seconds. Okay, again, starting out with underlining, then a little bit of drawing. 20 meters. This was a time of 10.2 seconds. Okay, again, we're doing velocity. Displacement divided by time. And this time we should know that displacement is he's going to the left. Maybe I should have underlined that. He's going to the left 20 meters. So I'm going to be putting negative 20 meters. Okay. And then time of 10.2 seconds. So the displacement is going to be 20 divided by 10.2. And it's going to be negative 1.96 meters per second. And this would be correct. Or you could put 1.96 meters per second to the left. Okay, either one of these would be good. Honestly, I'm gonna suggest doing the negative and not doing the left, but they're both correct. And the reason for this is for future problems, getting used to the negative will be better. But again, it doesn't matter. What is the speed? So speed similar to the displacement, but remember distance is only a positive thing. So going to the left 20 meters, we don't care it's going to the left, we just care that it's going 20 meters. And then what we get is 1.96 meters per second. Okay. Oops. Okay. Okay. Conceptual example here. A car is moving 50 miles per hour. We hear this all the time. The speed limit is 50 miles an hour, 60 miles an hour, 70 miles an hour, whatever. If it continues moving at the speed for 1 hour, how far would it have traveled? Okay, so if something is going 50 miles per hour, after 1 hour, how far would it have gone? Okay, so especially this per hour here, miles per hour, this should be telling you if something is going 50 miles per hour, every hour it's going 50 miles. That's what 50 miles per hour means. So what we have is this here. Maybe a little more tricky here. A car is moving 40 miles per hour. If it continues moving at this speed for half an hour, how far would it have traveled? Okay, so 40 miles per hour. However, we're not traveling for an hour anymore. We're going for half an hour. So that means if we're doing just half of this, that means we only travel 30 minutes or half an hour. That means it's only not going 40 miles in half an hour. It's going to go 20 miles. In the other, if it traveled the same speed, in the other half an hour, it would do the other 20 miles. So this is going to be 20 miles. Okay. Another one, a car is moving at 50 miles per hour. If it continues moving at the speed for 5 hours, how far would it have traveled? Okay, so we have 50 miles per hour. So in 1 hour, it'll go 50 miles. In 2 hours, it'll go 100 miles. In 3 hours, it'll go 150 miles. In 4 hours, it'll go 200 miles. And in 5 hours, it'll go 250 miles. Okay? Of course, you would need gas, and not everything is a straight path, and you don't always go exactly 50 miles an hour, but that's how it goes. Okay, so tips for the word problems are going to start getting a little bit harder, so these are the tips I very much suggest. Number one, as I've been doing, underline key information, things like left, right, numbers, anything that has a number, anything that says rest or drops or anything like that. Underline key information. This is a lot of times students struggle with word problems, and this breaking it down to these steps will help so much. Number two, draw out the problem. Luckily, in this PowerPoint so far, a lot of things are drawn out for you, but it's going to be really key that if it's not drawn out for you, that you learn how to draw out these problems. It'll help you a lot. And lastly, list your known variables and unknown variables. What that means is, like speed is equal to 2 meters, distance is equal to 5 meters. Oops, speed is equal to 2 meters per second. Distance equal to 5 meters. T is equal to question mark, which that's step 4. Find the unknown variable you're looking for. So list your known variables, like for example, speed and distance. That's what we've been doing so far. And list your unknown variable, like what you're looking for, time, in this scenario. 5. Select the formula that has the known and unknown variables. So it's like, okay, in this formula, we're using the formula speed equals distance over time to solve this. All right, so this is the key. Make sure you do this. A lot of times students love taking shortcuts, but it's only going to bite you if you do that. All right, here we go. Oh, calculate the value of done. Okay. Okay, so let's look at this example and try to implement those tips. So Jim and Harry are walking to the bus stop, which is 800 meters to the left of Jim's house. It takes them 1,200 seconds to arrive. As soon as they get to the bus stop, Jim realizes he forgot his lunch and runs back home, taking 600 seconds. He then rushes back, which takes him another 720 seconds. Okay, a lot going on here. Again, it's so crucial to draw out the problem. Luckily, a lot of it is drawn out for us, so we don't have to do too much. But if not, it's really important to draw it out. Okay. Okay. So, what was Jim's average velocity in meters per second for the entire trip? You should know velocity is equal to displacement divided by time, and then what we have here is the displacement, we should know, only cares about two things. There was a lot of back and forth that was happening here, but we don't care about the back and forth. Displacement only cares about where you started and where you ended. So Jim started at his house and he ended at the bus stop. Okay, he goes back and forth, but that's all that happened. So Jim's displacement from where he started is going to be negative 800 meters since it's going to the left. And now, what was the time that it took? So we know that the time it took, I'm just going to be adding everything up, is going to be this 1,200 seconds plus 600 seconds plus 720 seconds. Okay? And this will give us the velocity. 800 divided by parentheses 1,200 plus 600 plus 720 close parentheses, which is equal to 0.32 meters per second, or negative. So that's correct. So we could do that, or we could do 0.32 meters per second, or I should say positive, but we also say left. Okay, so either one. Okay, part B. What was Jim's average speed in meters per second for the entire trip? Okay, so this is going to be a bit different. Speed, again, remember, cares about uh, the distance. And the distance was, yes, he did go 800 meters there, but then he went 800 meters back, and then he went 800 meters back again. So speed is equal to distance divided by time, and his distance is 800 times 3, or also known as 2,400 meters. It's not going to be negative because, remember, speed is a scalar, distance is a scalar. It doesn't care about direction. And the time is going to be the same. This 1,200 plus 600 plus 720. And maybe we could just do that in the calculator for simplicity's sake this time. But that's going to be equal to 2520 seconds. And this speed is going to be different. So 2,400 divided by 2520 is going to give us 0.95 meters per second. Okay? Okay, that's the total distance and the total time. All right. So let's look at the next problem. Cindy is running a 5K, 5,000 meters, looking a loop for her first cross-country meet. Jim wants to make sure he is at the finish line when she finishes, but also wants to get a hot dog. Cindy usually runs with a speed of 4.3 meters per second. About how long does Jim have to get his hot dog? Okay. What is Cindy's average velocity when she finishes the race? Explain why Cindy's average velocity differs from her average speed when she finishes the race. Okay, so I've kind of underlined the key important information. I'm going to draw a little bit. So anyway, I'm just going to kind of draw a loop like this. So it's a loop and it is 5,000 meters, the loop. The distance is 5,000 meters. Okay. Her speed is equal to 4.3 meters per second. And the first question asks, how long does Jim have to get his hot dog? So what we're looking for is the time. So we're going to be doing speed is equal to distance divided by time. And if you guys kind of remember that triangle thing, anyway, different ways we can do this. We can just, if you know algebra, you can just switch this out. But if we know the triangle, I guess since this is one of the first problems, I'll do the triangle. So we have the triangle, speed, distance, and time. And since we're looking for time in this instance, we're just going to do this. Time is equal to distance divided by speed. Okay, or if you know how to do that algebraically, you can do that. Okay, so part A, we're looking for time. Time is equal to the distance, so that's 5,000 meters, divided by the speed, which is 4.3 meters per second. 5,000 divided by 4.3 is equal to, the time is equal to 1162.8 seconds. Okay, so that's how long Jim has to get his hot dog before Cindy finishes. Next question here is, what is Cindy's average velocity when she finishes the race? So remember, velocity is equal to the displacement divided by the time. However, we know what the distance is, 5,000 meters. But if Cindy does a loop, let's say she starts from here and then she goes all the way around, what happens is she started and ended at the exact same place, meaning her displacement is 0, meaning her velocity is equal to be 0. Okay, so we have 0 for part B. Explain why Cindy's average velocity differs from her average speed when she finishes the race. Well, the reason why is because of the distance and displacement are different. She didn't run in a straight line, she ran in a loop. Since the distance and displacement are different, that's why it's different from each other. Okay. Okay. Okay, let's look at this next example problem. Jim and Harry are having a race to get to Cindy's house. Cindy's house is 600 meters away. Jim runs as hard as he can with the speed of 5.3 meters per second, and Harry jogs with the speed of 8.2 meters per second. Harry's pretty fast. How long will Harry have to wait for Jim when he gets to Cindy's house? Okay, so these guys are running. Both going 600 meters. Oh, sorry, I should underline the key piece of information here. 600 meters away. And I'm gonna put Jim as number 1 and Harry as number 2 here. We know that Jim is going at a rate of 5.3 meters per second, and Harry here is going at a rate of 8.2 meters per second. Okay, so I'm gonna first figure out how fast Harry is going. So how fast is it going to take Harry to get to Sydney's house? Number 2. So Harry has a speed of 8.2 meters per second. He's going to be traveling a distance of 600 meters. And we're going to see how long does it take Harry to reach that 600 meters. Okay. So what we're going to do is speed is equal to distance divided by time. And this time, I'm just going to do the algebraic way. I know that time, if we put time over here, we can put speed in the opposite side. And then we're going to do time is equal to distance divided by speed. And now I'm going to do time is equal to the distance, which is 600 meters, divided by the speed, which is 8.2 meters per second, which gives us 73.17 seconds. Okay, so this isn't the answer. This is just how long it takes Harry to get to Sydney's house. Okay, let me use a different color for Jim. So I'm going to maybe redraw. This is Jim. He's going 5.3 meters per second. And let's figure this out. So Jim has a speed of 5.3 meters per second. He also traveled a distance of 600 meters. And we're looking for how long did it take Jim to get to Cindy's house. Maybe I'll even call this T2. Doesn't matter. Okay, speed is equal to distance divided by time. And again, we know time is equal to distance divided by speed. So time is equal to distance, which is 600 meters, divided by the speed, which is 5.3. Let's put this to our calculators. Minus, 600 divided by 5.3. And we get 113.2. 13.2 seconds. Okay, so again, this is not the answer yet. What we have to do is we have to find out, since Harry is faster, we know that he's going to be waiting for Jim. So we're just going to subtract these two. We're going to do 113.2 minus 73.17 to find out how long Jim was waiting. 113.2 minus 73.17, and we get 40.03 seconds. That's how long Harry's going to be waiting on Jim. Okay. All right, let's look at this next problem here. Cindy, Harry, Kiki, and Jim are participating in a 4x100 meter relay race. Cindy burns everyone and runs the first 100 meters with a speed of 8.7 meters per second. Harry gets the baton and runs his 100 meters in 12.8 seconds. Kiki runs her 100 meters with a speed of 7.2 meters per second. Jim almost fumbles the baton but is able to hold on to it. With only one person in front of him, Jim runs as fast as he can and finishes the last 100 meters in 12.4 seconds. Who ran the slowest on the team? What was the average speed for the entire team? Okay, so lots of important information here, or lots of information, I should just say, in general. Okay. So let's first try to understand what's going on. A lot of times students will look at a problem like this and they don't even know where to start, where to begin. There's just so much going on. But again, we need to take it step by step. We need to break down important pieces of information and then go from there. So let's just first try to understand what's going on. This is a relay race, meaning that Cindy is going to travel 100 meters, do distance 100 meters, and pass the baton to Harry. Harry is going to travel 100 meters and pass the baton to Kiki. Oh, actually, you know what? I'm going to do this in a different color. Okay, let's see. Let's do this dark. Harry's going to pass the baton to Kiki. And go 100 meters. And then Kiki is going to pass the baton to Jim and go 100 meters. And then Jim is going to try to finish the race traveling 100 meters. Okay. So let's see some other key piece of information that we know. Start with Cindy. So we know that Cindy burns everyone, runs the first 100 meters with a speed of 8.7 meters per second. So her speed is equal to 8.7 meters per second. Okay, we know her speed. It doesn't seem like we know her time. So I'm just going to put time question mark here. Even though it doesn't seem to ask for it, I'm just going to write that down for now. Okay, and now let's look at Harry. So Harry gets the baton and runs 100 meters in 12.8 seconds. So we know the time for Harry, 12.8 seconds, but we don't know the speed. Okay. And now let's look at Kiki. Kiki runs her 100 meters with the speed of 7.2 meters per second. So we know her speed, which is 7.2 meters per second, but we do not know her time. Jim runs as fast as possible, 100 meters in 12.4 seconds. So we know his time, but we do not know his speed. Okay. Okay, so again, now this should be getting more manageable. What we're looking for is what everyone's speed is at first. And we have two people's speed. We have Cindy and Kiki, but we need to figure out what Jim's and Kiki are. Oh no, Jim's and Harry are in order to do more of this. So once you're able to, do more, once you're able to break it down, the problem becomes a lot more manageable. So let's look at Harry's. So Harry, we're looking at his first speed and distance divided by time, and we know his distance is 100 meters divided by time, which is 12.8 seconds. So we know, oops, that he ran his in 7.81 meters per second. Okay. So now we know what his speed is. 7.81 meters per second. Okay. And now let's figure out what Jim's is. So Jim, his speed is equal to distance divided by time. The distance he traveled was 100 meters, and the time was in 12.4 seconds. So we already know it's faster than Harry, actually, in this instance. That's why you run the race. And that was in 8.06 meters per second. Fast, Jim, fast. He's been training. Okay, so now when we look at all of this, we look at each speed and we figure this all out. We can look at each of the speeds and see who ran the slowest. And we can tell that who ran the slowest is actually going to be Kiki. So Kiki ran the slowest. What was the average speed for the entire team? Okay, so you might be tempted, okay, we got everybody's speed. Let me add them all together and divide by 4. However, that's not exactly the best way to do this. Let me do this in black. So what the average speed is equal to the total distance ran by the team divided by the total time by the team. So the good thing is we have the time for everybody. Everybody ran 100 meters, so that total distance is going to be 400. But we don't know what the total time is. So we don't know the time by Cindy and Kiki. So let's kind of figure those things out. So first of all, let's look at Cindy. I guess I'll go over here. Cindy, we know that time is equal to distance divided by speed. And the distance is 100 meters. And the speed she traveled at was 8.7. So we know her time will be 100 divided by 8.7, which is 11.49 seconds. Okay. We could also add that right here. 11.49 seconds. Okay. And now we have to find what about Kiki. So we know Kiki here, time is equal to distance divided by speed. And the distance is 100 meters divided by 7.2 seconds. And that's 13.89 seconds. So now we have all the times and we have all the distances. So let's use this now to figure out what the average speed is. Oops. Okay, I'm going to do this in black again. Okay. So this is going to be total distance. It's going to be 400 meters, 100 plus 100 plus 100. And then the total time, which I'm going to put in parentheses, I'm going to start with Cindy, is going to be 11.49 plus 12.8 plus 13.89 plus 12.4. Okay, now let me just put this in the calculator. 400 divided by parentheses 11.49 plus 12.8 plus 13.89 plus 12.4. And what do we get? The average speed is 7.91 meters per second. Okay. All right, guys. That's it with speed and velocity. Next time, we're going to be doing problems involving graphs, position versus time graphs. So I look forward to that. Thanks for watching, everyone.